Welcome, dear friends of protection, control and electrical engineering. Today we're gonna do a wattmetric ground fault protection test of an MCA4 from SEG. As a test set, we use a brand new SVERKER 900 from Megger. Have fun and let's go! Okay, let's start with our protection relay. We have an MCA4 from the German protection relay vendor SEG on the table, which serves as a complete solution for the directive compliant connection of decentralized generation systems, or also excellently for the protection of feeders. The relay is characterized by high measuring accuracy and high reliability, and also has an independent certified component certificate according to the IEC 60255-1 by the KEMA Institute. We are often asked what is actually the difference between an MRA4 and an MCA4. Well, the R stands for relay and the C stands for control. While one switching device can be controlled by the MRA4, the MCA4 has the extended control capability and up to 6 switching devices can be supported. Our comparison also shows that the MCA4 version has a larger display. Okay, today, as I said, we are testing the MCA4 from SEG and initially assume that we are in a small 20 kV medium voltage network, that all star points in our network are operated in isolation, and that the resulting earth fault factor is around 1.7. The expansion of the network should be around 6 miles. The resulting capacitive ground fault current is then around 26 amps. The present network configuration results in the selection of the sinus phi method as the protection algorithm, and we have implemented our protection system as follows. On the secondary side, we measure the triangular windings of our 3 voltage transformers connected in an open triangle to get our voltage, and the 3-volt zero current will be measured with a 60 to 1 amp split coil transformer. We have parameterized the protection function itself with a current setting value of 210 milliamps and a typical voltage setting value of 30 volts. The delay of the timer is 100 milliseconds and the sinus phi method is activated. Before we start the test, let's take a look at the test setup. With the SVERKER 900, we trigger the binary output 1 of the MCA4, provide the test voltage and also feed the test current into the MCA4. Please be careful that both current and voltage are connected with the proper polarity. So let's go. In the first step, we do a plausibility check to see whether the algorithm is working as expected. We assume a full ground fault in phase 1 and apply a voltage of 100 volts, which is the typical European value. We chose the angle to 180 degrees since the zero voltage always has the opposite sign to the pre-fault voltage of the ground faulted phase. We chose the current with a full trigger value, or let's say tripping value of 300 milliamps. As a reminder, our setting value is 210 milliamps. Since we first want to test an error in the reverse direction and show the stability or the non-triggering of the directional element, we chose a current angle of 270 degrees. We remember the theory: the capacitive ground fault current of the faulty feeder flows in reverse direction through the current transformer and appears as an inductive current. Accordingly, a current lagging by 90 degrees must trip, and a current leading by 90 degrees has to stabilize the directional algorithm. Here we go. We push the button and see that the ground fault is detected, but our directional algorithm remains stable. In the next step, we chose a current angle of 90 degrees and repeat our plausibility check and are very happy because our directional algorithm trips. The nice thing about the SVERKER 900 is that we can always see the phasor diagrams of our test parameters on the colored touch display. This is an excellent experience and outstanding visual support during the test. With the present test point, we can now evaluate our timing element directly. To do this, we activate the trigger and start the test again. The tripping time of just over 100 milliseconds can now be noted and evaluated, and we can go over to the pickup values. Here we go over to the ramp instrument of the SVERKER 900 and briefly program the test sequence. The voltage should be constant at 100 volt and 180 degrees over the entire test, while the current is ramped at a constant angle of 90 degrees in 1 milliamp steps from 200 milliamps to 220 milliamps. We expect our triggering at 210 milliamps and start our test. We receive a trigger at 209 milliamps, which is within the vendor's tolerance of plus minus 0.5%. Since the capacitive ground fault current also has slightly resistive components in isolated networks, it is also advisable to check a slightly ohmical inclined characteristic. The main cause here is the fault resistance itself. For this purpose, we repeat our ramp test with a constant current angle of, let's say, 80 degrees. Here we see our expected tripping reaction of the relay. Since we are also interested in the release value, we now drive a reverse ramp with a current angle of 90 degrees and set a start value above the pickup value. For example, we chose 220 milliamps as a start value and 200 milliamps as an end value. To make sure that the SVERKER does not lose control when the test starts, we have to change the trigger from normally open to normally closed. The result is a release value of 204 milliamps or a release ratio of 0.98. As a reminder, the release value is calculated from the ratio of the release value to the pickup value, and it is dimensionless. Great! We are now doing an analog ramp test for the voltage pickup. This time we keep the current value constant over the pickup range. The implementation is very easy and we won't repeat it now. Maybe a quick note at the end. Since insulation failures usually have a sudden character, it is also useful and quite common to do our tests shown here with so-called pulse ramps and to simulate zero states between the individual test points. Thank you for watching, see you soon and goodbye.